All right, the last lesson in Learning Guide 5 is Lesson 6 called Optimization Problems. Now, this is really switching gears from what we have been discussing in the last few lessons, which is drawing graphs. This is, again, really switching gears. What we're looking at now is basically the application of derivatives. So why do we learn about derivatives? Like, what good are they in real life? And this is actually, these optimization problems really shows clearly why derivatives are so amazing. If you own a business and you want to find the maximum profit over a certain amount of time with other things, derivative is going to help you. If you want to look for the minimum cost to build a pipeline or the maximum volume of a container with a minimum amount of material, that is where derivatives are actually applied. So we're going to look at these questions, and they might actually look very familiar back from Math 20-1. And we're going to show you kind of a different way than you learned in Math 20 using derivatives to solve these, which is really cool. So if we look at information that we talked about in this learning guide, remember, maximum or minimum value occur at critical values in my first derivative. That's that first derivative test. So remember, we find the first derivative, we set it equal to 0, x is going to be equal to my critical value, and that automatically is a maximum or a minimum. Okay? It could also be an inflection in some cases as well. All right, so let's look at the first one. Number 1, find two numbers whose sum is 34 and whose product is a maximum. Again, this is a question right from Math 20. So basically, number 1, we all know to create our equation, first of all, right? So find two numbers whose sum is 34 and whose product is a maximum. Okay, so pretty basic equations. Now, if you remember from before, what we have to do is obviously combine these two equations, and we can do that by substitution. So let's solve for one of these variables. Let's say y. It doesn't matter which one. So we're going to say y is equal to 34 minus x. And if we substitute that in, now we've got one variable, okay, and one equation. So I've got basically 34x minus x squared. And that's going to be equal to my maximum or my function. This is the function that we're going to be using here. Now, number 2, remember I'm looking for the maximum product. So maximum, automatically when you see maximum or minimum, you want to think critical value. So let's find that derivative. So it's going to give us 34 minus 2x. And then remember, we just set that equal to 0. So I've got 2 times 17 minus x. So x is going to be equal to 17. Now, x is obviously one of our numbers, right? The question is saying find two numbers whose sum is 34 and whose product is a maximum. Well, if we already know that x is equal to 17, we can very easily find y. And we can do that by using the equations up here. We know x plus y is equal to 34, or more importantly, y equals 34 minus x. So y equals 34 minus x, so therefore y is going to be equal to 34 minus 17, so y is equal to 17. Okay, so therefore the two numbers are 17. All right, so pretty basic, and again, a nice application of derivatives. Let's look at another one. A farmer wants to enclose the largest possible rectangular pen for his chickens, so think maximum, right? Using 300 meters of fencing. Find the dimensions of the rectangle if he plans to use the barn as one of the sides. Again, right out of Math 20. So we know, let's call these x's and these y's. Remember, the barn doesn't matter. So if I know that he's got 300 meters of fencing, well, number 1, my equations must be 2x plus y is going to be equal to 300, right? We're talking perimeter there. And right away, we can easily solve for one of our variables, which would be y. So that would be 300 minus 2x. And the question is saying he wants the largest possible 10. So if we're talking about the largest possible room, basically we're talking area, right? So the area of this rectangle is going to be x times y, and that, again, we want the biggest area possible. So let's plug in our values. 300 minus 2x, and again, that's going to be equal to our function, or our maximum in this case. Now, if I'm looking for the maximum, let's make this look a little bit nicer. And then number 2, remember, we just find our derivatives, or our critical value. So we find that first derivative, 300 minus 4x. In order to find the critical value, we set it equal to 0. So we can factor, and we're going to get x is equal to 75. Sweet. See how much quicker this is? Wow, if only you knew this in Math 20. All right, so if we go back up, it's saying find the dimensions of the rectangle. Well, if we already know that x is equal to 75, now our third step, guys, is we can solve for y. 300 minus 2 times 75. That's going to give us 150. So what are the dimensions? Dimensions are 75 meters by 150 meters. Okay? All right. Let's keep moving. Next one is a box with a square base and open top. And again, please remember, even though sometimes I forget to say it, pause, fast forward, make sure you're trying these on your own. Learn, learn, learn. All right, a box with a square base and open top must have a volume of 4,000 centimeters cubed. Find the dimensions of the box that minimizes the amount of material used. What does that mean, amount of material used? Well, that has to be talking about our surface area. All the amount of cardboard or whatever it is on the outside has to be a minimum value. So let's keep that in mind when we're coming up with our equations. All right, so the first step is our equation. Now, the first one is talking about volume. So how do I find volume of this box? Well, remember, it's just your area of your base times your height. Okay, so the area of the base times height, we don't know what height is, so let's just call it y. So the area of your base times your height. So volume, which is 4,000, must be equal to x squared times y. And we can easily solve for y if we need to do so, right? Now, surface area is the area of all the surfaces. Now, we don't have a top on this, so I'm just looking at my x squared plus the side here, the area of that has got to be just x times y, and there's 4 of them. So let's do 4xy. And remember that we want the surface area to be a minimum. So that means x squared plus 4xy must be equal to a minimum value. Now, this is obviously the important equation, right? This is equal to the minimum. So this is the one that we can manipulate for one of the variables. And we just said, well, y is easy to solve for. It's just going to be 4,000 over x squared. So now let's plug that in. So I know that x squared plus 4x times 4,000 over x squared is going to be equal to my minimum. Let's kind of simplify this. So x and the squared is going to be gone. So our function that we're going to be working with is just going to be x squared plus 4 times 4,000 is 16,000 over x. All right, so the first step, we found our function. Next one, remember we're looking for our critical values. So we want to take the derivative of that. So that's going to become 2x plus, and you can do this in a couple ways. You can either make it 16,000 times x to the power of -1, or you can use the quotient rule. It's completely up to you. If we use the quotient rule, let's say this times the derivative of that is 0 minus, so I'm just going to change that to a minus, 16,000 times the derivative of x is 1 over x squared. Okay. Now, if I set this equal to 0 in order to find my critical value, Okay, what we can do is just try and get rid of that fraction. So get rid of our denominator of x squared. So I can multiply this by x squared. That's going to give me 0 is equal to 2x cubed minus 16,000. And now we can easily solve for x. 16,000 is equal to 2x cubed. Divide by 2. 8,000 is equal to x cubed. Cube root 8,000. And you're going to get 20, and I believe it's centimeters. Okay? And once you have one of those variables, we're sorted. Let's go back up. Look at this equation where I've got y equals 4,000 divided by x squared. So y equals 4,000 divided by x squared. So that must mean 4,000 divided by 20 squared, and that's going to give me 10 centimeters. So the question is saying find the dimension of the box. Well, the bottom, so I'll just say therefore the dimensions. The bottom has to be 20 by 20, and then the top would be 10, and all of those in centimeters. There you go. All right, so hopefully you guys are finding this okay so far. If not, just pause, try some more, go slow, rewind, ask the help desk, all those good things. All right, and the last question here is number 4. And as always, in the blue there, it's saying watch the domain for certain scenarios. So guys, just keep in mind, very logic, if you get a negative value or a 0 for a side length or something like that, that's always a little bit of a warning. So just keep that in mind that obviously you're not going to be including those in your final answer. It's saying for number 4, a box, again with an open top, is to be constructed from a square piece of cardboard, 3 meters wide, by cutting out a square from each of the 4 corners. So these are being cut and then bending up the side. Find the largest volume that such a box could make. So obviously we're looking for the maximum volume. All right, so first we need to figure out, now this diagram is a little bit misleading. I don't just want you to call that X. What this question is saying is that we know that this whole length was 3. But what's happening is they're cutting out these little squares, and we don't know the dimensions of the square. So let's just call that X. And there are 2 of them. So if I'm looking at the length that's actually given, I know that that must be 3 minus 2x. Right? Because I'm subtracting those 2 x's. Same as here because it's a squared. Now, if I think logically about what the height of this box must be, well, if I'm cutting out this x and then I'm folding it up, that height must be x, right? So try and visualize, and if you cannot visualize it, take your piece of paper, not your notes, but take another piece of paper and, rip off 4 corners and then fold it up, and you'll see that what you've ripped off actually becomes your height, which is kind of cool. All right, so let's think about equations. Now, first we're talking volume, right? So if I'm looking for volume of the box, remember that's the area of the base times the height. So your volume is going to be the area of the base, so that would be 3 minus 2x times 3 minus 2x, and we're going to times that by our height. And if you notice here, guys, I only have one variable that appears here, which is great. So I don't need 2 equations, which is a change from the last couple of questions. So let's look at this. I've got my volume. Let's simplify it. If you FOIL that out, you're going to get 9 minus 12x plus 4x squared times x. So our volume is going to be 9x minus 12x squared plus 4x cubed. And we're good to go, right? Now remember, we want to find the maximum volume. So this is our function, and we need to find the critical values of that function. So I'm going to take my v prime of x, and that derivative is going to be 9 minus 24x plus 12x squared. And to find the critical values, we set that equal to 0. So I'm going to factor out a 3. 3 times, oops, whoa, that's a lot of 3's there. Okay, so I'm going to factor this out. And when I factor out the 3, I'm just going to change the order of these guys. So 4x squared minus 8x plus 3, just so we can use our PSA2 method. Remember PSA2, 4 times 3 is 12. The factors of 12 that add to negative 8, so that's going to give me negative 6 and negative 2. So 0 would be equal to 3 times, and I'm going to rewrite it, so 4x squared minus 2x minus 6x plus 3. Continue to factor. I can factor out a 2x, 2x minus 1, minus 3 times 2x minus 1. Okay, and factor. 2x minus 3, 2x plus 1. Oops, sorry, 2x minus 1. And to solve for x, obviously we're going to have 3 over 2 and 1 over 2. Both positive, so both possibilities of an answer, right? So remember how we were kind of saying watch the domain? Well, x could technically be equal to both of these, 3 over 2 and 1 over 2, but we probably only have one as an answer. So let's go one step further, and it's saying find the largest volume. So we know that volume is this right here. So if I'm looking for the largest, let's try both of these numbers, both of these critical values.